file or other like mergers which it can detect from your browser history. And a lot of location-based applications are coming up. For example, recommendation systems. They are like Microblog is one of them. Foursquare. They're all like location-based services coming up in mobile applications. iPhone store has already more than 7,000 location-based applications, and Android market is also catching up. One of the motivations behind it, like they're saying that in future this industry is going to grow very large, both based on the number of users and the number of money involved. And another social survey claims that more than 70% of the calls originate from indoor environment, and 80% of time people use their smartphone from indoors. And all this, most of the latest smartphones nowadays are embedded with these time use sensors like accelerometers, gyroscope, magnetometers, and other sensors also coming up. So these kinds of sensors are giving us new opportunities for sensor-driven mobile computing. For location-based applications, for example, we need a way to localize a user within an environment. And the current technologies, for example, GPS, which is very accurate, it's like up to 10 meters, but it's very, very less energy efficient. And one of the major drawbacks for it is that it doesn't work indoors. Then a lot of Wi-Fi-based solutions are getting popular. They are more common for an indoor environment. I will talk about the techniques we might use later on. But one of the drawbacks for using a Wi-Fi-based localization is that a lot of training is required, a lot of calibration is required for the system. Then GSM-based solutions are also available, which are not that popular. One of the primary reasons is like the accuracy is like very less. Then when we talk about like the indoor localization systems already available, for example, GSM-based or Wi-Fi-based, they don't work in an environment where there's no Wi-Fi infrastructure. Like if there's no Wi-Fi, you won't be able to localize or position a user within an environment. For example, the one-tunnel system is one of the environment because there's no Wi-Fi, you cannot position a user within that area. But let's say we have this tunnel map. There's no Wi-Fi within the tunnel passage, but you can detect Wi-Fi signals at specific positions. For example, whenever you enter the tunnel, there sometimes sporadically you can observe some access points on those locations. So one of our hypotheses was, can we use our smartphone sensors, for example, accelerometers and gyroscopes, and magnetometer, to make a pedestrian dead reckoning system and an inertial navigation system, and use these sporadic Wi-Fi signals as landmarks to correct or position the user. So we start off with this hypothesis. I will talk about like the pros and cons of these sensors, which are now in most of the latest smartphones. Like the gyroscope started with iPhone 4, and now a lot of latest smartphones have it. Accelerometers is usually the smartphones use it for tilt and orientation. Accelerometers, basically the 3D accelerometers provide you the acceleration in 3 dimensions. And you can use this sensor to detect, for example, the steps you are taking. For example, a lot of latest like pedometer applications, they use this for like if you're running, for jogging, if you're walking, to count the number of steps you take. But it had some cons. For example, it's very sensitive to shaking and vibration. So if you have random movements, it can detect as a false step. Another con is like you cannot differentiate between acceleration due to gravity or acceleration due to acceleration. For example, if you're holding the phone like this and you have 1g acceleration in this direction, it won't be able to differentiate if you went in this direction or in this direction. So you cannot distinguish that, just based on acceleration. On the other hand, gyroscope calculates angular velocity, and you can basically maintain or estimate an attitude of the device in 3 directions, like the yaw, the roll, and pitch. But the con for a gyroscope is that over time, because it uses integration to calculate the orientation, so over time the error accumulates. So somehow you have to reset it after a while. Magnetometer, on the other hand, all the magnetometers in the smartphones, they provide you magnetic readings in 3 direction, and they also provide you with a magnetic heading, and they can also provide you with absolute heading if your GPS is accessible. On the other hand, magnetometer alone in indoor, especially in indoor environment, is very, very noisy because of buildings, maybe some metals in the walls. It's very, very noisy. So these are the pros and cons of these sensors. And one of the other goals for the indoor positioning system is that it has to be accurate. Like it should be able to tell you where you are. It should be very responsive. Like it should tell you where you are like as soon as possible whenever that requires. It should be energy efficient and scalable. Like you can employ your system anywhere you want and with ease. This is basically energy, the power consumption of these different technologies. Accelerometer is the blue one. You can see accelerometer and compass both use very little energy compared to GPS, which is the black one, and Skyhook. Skyhook is the technology Apple basically uses. It's based on both Wi-Fi, GPS, and GSM. So it's like a hybrid technology they use to estimate the position. So you can see basically these two sensors, accelerometer and compass, they use very less energy. So this was our research question, like can we use these advanced sensors in smartphones and assisted by RF sporadic RF signals in different locations to locate a user. For example, if a user is walking in this path, so we can detect the direction the user is walking and we know the direction of the user. So based on this path, we can match it with a map and see if and predict if the user is in this path or not. And then also use position correction based on this Wi-Fi access points. If there are, for example, similar paths, we can distinguish between two based on the Wi-Fi signals. So this is the overall proposed system design. We take, because we are considering both the pros and cons as I mentioned, magnetometer, it is very noisy compared to gyroscope. So we basically, from the magnetometer, but gyroscope basically cannot tell you the absolute heading. Like it can tell you only if I was here, now how much have I turned. It cannot tell me if I'm 30 degrees to the north, whereas magnetometer can. So we basically use magnetometer just for the initial heading calculation, and then we rely on gyroscope to tell me where I'm going and where I'm turning. And then I use accelerometer for step detection and as a step counter. So both these things, like the number of steps taken and the direction, I can basically make a user trail where the user is going. On the other hand, Wi-Fi is used as landmarks. So basically, this pedestrian directing system is used basically to create a belief map of the environment, like where I am with some probability, and then use this belief to display it on a user interface, a map-based user interface. This is just a small introduction how the belief system works. Basically, this kind of thing, theoretically, in robotics, they use this kind of theories. For example, let's say a robot is, initially the robot doesn't know where it is in the environment. And after moving a certain distance, the robot still doesn't know where it is in the environment. It just knows that it has moved this much. After moving, let's say he has a camera and he can see that, okay, I'm in front of a door. So now the belief system says that I am either in either of these locations. So I'm in front of this door, so I'm like in these three locations, but it cannot differentiate where I am, in front of which door I am. But after moving, let's say a few meters, it stops, and then again it sees another door. Now it can, because of movement, the probability belief shifted because it knows that I moved this distance. But now after the camera captures again that he's still in front of the door, he can more accurately guess that, okay, I'm in front of the second door. So basically this kind of techniques are used in robotics. And we're going to use the same techniques for mobile positioning. This is basically the base filter which uses this technique. The second step is called prediction. From the movement of the robot or the movement of the user, you can predict where you can be, like in the environment. And the third step is called the measurement update. That after moving after the control, you observe where you are and try to relate that if your belief is correct or not. And this will basically updates your belief through the measurement. Okay, this is basically the map of our computer science department, and we tested this our system in both computer science department and the mining terminal. These points are basically anchor points. We created these small grids along the location. They are like 3 meters by 3 meters, and each anchor point basically represents this grid. And this is like one of the belief state, these are the possible location a user can be in an environment. Okay, this is